Okay, in this video, I want to talk about effect sizes. What we really care about when we do science and look for whether two groups differ or whether some treatment has an effect, we care about how big the difference is, how big the effect is, not just whether it exists at all. Like, you're probably used to the idea that statistical tests tend to give you a p-value that we use to determine statistical significance. Basically, when we say a result is statistically significant, it tells you if we think there's an actual effect. We rejected the null hypothesis, and so we accept the alternative hypothesis. Basically, the p-value we calculated was the probability that we would get sample results as extreme as our sample, as extreme as the sample we got, if the null hypothesis was true and there was no effect. If we get a really low p-value, we're saying it is really unlikely we'd have gotten these results if the null was true, so we reject the null and we call that statistically significant. And we conclude, yeah, we think there is an effect. But notice, none of this tells us how big the effect is. What if we find out our new drug has a real effect? Maybe despite all the dangerous side effects, our new drug does cause a teensy tiny improvement in depression that's almost imperceptible. Like maybe on a scale of 1 to 10, depression scores go down 0.003. Like at this point, you might not really care that that effect exists, that the drug does something, that it's statistically significant. You probably care more that the effect is so small it's basically meaningless. So in addition to using statistics to ask about statistical significance, we also need to think about practical significance. Is the effect big enough to matter? And this is a separate question because it's asking something that a p-value doesn't tell us anything about. It's asking how big the effect is. So to judge practical significance, we need to also calculate an effect size, which is just going to be a number telling you how big we think the effect is. We need this piece of information in order to make our own personal judgment of whether the result has practical significance. It is entirely possible that the effect is so small we don't care, even if our stats test cranked out a low p-value and we rejected the null and concluded there's a real effect. Which means anytime you report a statistical result, you really should be reporting two pieces of information. A p-value, yes, and an estimate of the effect size. In shorthand, you can kind of think of these things like this. Statistical significance only tells you, is the effect real? Did we reject the null? But practical significance is asking, is the effect big enough to be meaningful or interesting? Which requires knowing the effect size, which is kind of like how big is the effect. So we could define effect size as basically a measure of the strength of the phenomenon, the magnitude of it. Like, imagine we're comparing two groups to see if there's a difference between them. Like, just imagine there's two populations out there. Maybe it's men versus women on some dependent variable, or people who get the new surgery versus people who got the old surgery, or whatever kind of comparison we might do. You can visualize effect size kind of like this. Imagine the yellow line is the distribution of one population, and the purple line is the distribution of, like, everyone in the other population. The distance between their average, between the center of those two distributions, that would be a good way to think about effect size. So if the two distributions almost entirely overlap, then we'd say the effect size is pretty small, right? There is a difference between them, but not much. And in that case, pretty much everyone in the purple group is going to be very similar to pretty much everyone in the yellow group, and vice versa. But if they're further apart, if the mean of one group is way higher than the mean of the other group, then there's a larger effect size, a lot more difference on average. So like in the bottom right example here, most of the people in the purple distribution are higher than just about all of the yellow people. So a big effect size in that case. You can see how this is useful information once we're confident the effect is actually real and not a false positive. But to make it real clear, let's look at an example. In a given country, like the US for instance, let's think about the height of all the adult females and all the adult males. So everyone, not just a sample, but the whole population of everyone in the US. Let's just imagine the population average for females is 64.3 inches for height. So we'd write that as mu equals 64.3 because we use mu, the Greek letter mu, for a population's mean. And for males, the population average, let's say, is 69.7 inches, we'll say. But of course, within females, there is variation, with some people unusually short or unusually tall, as we see in that left curve for the women curve there. But, most of the women are near the middle of that distribution, near the average of 64.3 inches. And likewise, for males, for the second curve on the right here, there is a lot of variation. Some are quite a bit shorter. In fact, there's a lot of males in this part of this distribution here that overlap with the height of a lot of females, right? And some males are quite a bit taller. In fact, the tallest males, there's probably quite a few more than the tall females, and maybe some that, females don't get that tall. But the bulk for men are not too far from the population mean of 69.7 inches. Like most men fall right around that average. Now, we can't really go out and measure every single person in the US, so we can't really know these population values. We can't know these exact distributions in the whole population. But if we somehow knew this information, we could say precisely what the effect size is. We could say the male average is 5.4 inches above the female average. So we would say the effect size here in the populations is 5.4 inches, a mean difference of 5.4 inches, right? A difference in the means. It's easy to interpret. It clearly tells us how far apart the center of these two distributions, these two populations are. So this is the kind of thing people are talking about when they make marketing claims like the bullshit you see here. When they claim you'll lose 30 pounds, they're saying not just that their product will help you lose weight, which would be like, oh, we're claiming there's an effect. That could be a meaninglessly tiny bit of weight, right? But no, they're saying you will specifically lose 30 pounds, which is a huge ass effect size for something like weight. Now, obviously, companies like this are often totally bullshitting you and making false claims that aren't backed up by actual research or by kind of really shitty research. But the point is, the 30 pounds claim here isn't just saying there's an effect on weight. It is claiming an effect of a particular size, of a particular magnitude. When you look around, you will start to see this all the time, and that's because we humans obviously don't just care that there's an effect of something or that there's a difference between, the population of people on Cinsa and the population not on Cinsa, which again is likely bullshit in this case. But we generally also care about how much of a difference there is. Now, thinking back to how null hypothesis significance testing works, we're generally comparing two possibilities. There's the null hypothesis, which is some way of saying there's not an effect, or at least not in the direction we're interested in, versus the alternative hypothesis, where the null is false and there is some effect. So how big is the effect size? Well, if the null hypothesis is actually true, not just in our stats test, but like true in reality, if there's no effect, then the effect size is 0, right? But if the null is false in reality, then there is some effect. But the thing is, we might not know what it is. We may not know how big it is in reality. We just maybe want to try and estimate it. So think of it this way. What we would really love to know, if it was in any way possible, would be the true and actual population effect size, which we could just calculate as like the difference we found between the two populations or groups, like the average of our treatment group minus the group that didn't get treatment. Like what's the average of people who got our new drug, and subtract what we would see if the drug had no effect, if they're identical to the control group. In other words, subtract what we would expect if the null hypothesis was true. That's the effect size. The difference between, what the population average would be if the null was true, and the population average in the actual treatment population. If there's no difference, then the subtraction comes out to 0. We'd say the treatment doesn't work. There's no effect size. If there's a big difference, though, then we're looking at a big effect size. But the problem is we don't know the actual population values. So we can't calculate this true population effect size. Instead, we calculate our best guess of it, which is what we'll call the estimated effect size. This is something we can calculate from our sample. And this is just defined as our sample's mean minus whatever we'd see if the null was true. Like, if we know that people in general have an average memory score of 50 on some memory test, then the null hypothesis says that people taking our new memory pill will still have an average memory score of 50. That's the null hypothesis, because the null hypothesis is that the new memory pill doesn't work. But then, let's say we take a sample of people that we gave the pill to, and if they score 55 on average, that is 5 above the null hypothesized value of 50. So that would be an estimated effect size of 5, right? Our sample was just 5 above whatever the null hypothesized. So we say it's estimated because we don't know for sure that the whole ass population would go up to an average of 55 if they all took this new memory pill. But our best guess of what the effect size would be comes from our data, from our sample, from our best guess, and our best guess would be whatever the effect size we found in our sample was, which is 5. So we just kind of want to acknowledge that it's an estimated effect size since we did estimate it from our sample. So conceptually, we could think of estimated effect size as the difference between our sample mean, which we're going to use as an estimate of the whole treatment population's mean, even though we don't know the whole population, the difference between that and the null hypothesized mean. So for example, if the null hypothesis is that a certain group has a population mean of 100, then the alternative hypothesis that has to pair with that would be that the group does not have the population mean of 100, right? Because the null hypothesis and the alternative hypothesis always use the kind of equal and opposite, like the paired complementary signs here. So if we have an equal sign, then we'll have a not equal sign, right? Now, let's say we take a sample of this group, and our sample has a mean score of 102. Does that mean that this group as a whole population would have a population mean of 102? Not necessarily. But that is kind of our best guess of what the whole population mean would be, because that's kind of the only information we have. So we would report this as an estimated effect size of 2. And that is our best estimate of the real population's effect size. But we want to acknowledge it's an estimate, right? And again, just as a side note, an important reminder here that effect size is separate from whether a hypothesis test turns out to be statistically significant. So for that question, we would need a p-value. But like in this example here, it might not actually end up statistically significant. Maybe the p-value isn't low enough to be below the threshold. We don't reject the null. We don't call it statistically significant. If that happens, in that case, we don't want to take this estimated effect size very seriously, since we wouldn't even be confident there is a real effect in the first place. Now, let's zoom out for a moment to just think about effect sizes in general. Is a mean difference of 2 very meaningful? Like, does it have a practical significance if we find that our treatment causes a difference of 2 on average? Or if we find that two groups have a difference of 2 in their average score? Is 2 a lot? Now, obviously, it depends on what thing we are talking about. So just for example, maybe you would judge a difference of 2 IQ points between Mountain Dew drinkers and the general population. Maybe that's not a huge deal to you, right? You might not consider that a big effect of 2. But if the general population has an average of 10 fatal heart attacks per 10,000 people, and we find that drinking Mountain Dew increases the death rate to 12 per 10,000 people, that difference of 2 might be important, right? So sometimes an effect size of 2 feels like a lot, other times it maybe doesn't very much. And likewise, an effect size like we found earlier with height of 5.4 inches in height between males and females, yeah, that's nice and straightforward to interpret. It's clear what 5.4 refers to there. But then compare that to something like an effect size of 2.7 between males and females on the Beck depression inventory. Again, on its own, that's pretty straightforward to interpret if you've seen the Beck scale and you know its range. But how can we compare them? Like, if these numbers are true, if these are the real numbers here, in which domain does gender have a bigger effect? We have a 5.4, we have a 2.7, but is 5.4 inches more of a difference than 2.7 Beck depression scores? Like, it's like comparing apples to oranges instead of apples to apples. We can't compare those effect sizes directly across different domains, which is kind of an annoying problem. And a general solution to that problem is to divide the effect size by standard deviation. And that gets us what we call a standardized value. It's kind of like a z-score of the effect size, if you're familiar with that terminology from statistics. It just tells you how many standard deviations the effect size is. Like how many steps of the standard deviation is your effect size. So the standardized version of effect size, where we take it and divide by the standard deviation, that is called Cohen's d. It's really common to report this for the effect size in research studies. You'll see it a lot alongside the p-value that tells you if the effect is real. So if we wanted to calculate Cohen's d, this standardized version, we would just take that effect size we had before and divide it by the standard deviation. So if we were somehow working with a whole population, then the standardized effect size would just be that population effect size that we had before, divided by the population's standard deviation, which we use this Greek letter sigma in the denominator here for standard deviation. But of course, we don't normally work with whole populations, right? So we can't usually calculate this. Instead, what we have is our sample data. And we can see the effect size in our sample and divide that by the standard deviation in our sample. So we could call that maybe the standardized estimated effect size, right? Because we can calculate the estimated effect size and then we can divide to standardize it. So in this case, instead of Cohen's d, we might call this our estimated Cohen's d, or just estimated d for short. It's the estimated effect size that we got from our sample, that's the top part, but now divided by the standard deviation, which is literally just the standard deviation in our sample. And this is all information that we have access to in a real research study. So this is what we would use and report in real research, what you'll see all the time. You'll often see researchers report a Cohen's d value for the effect size, but in your head, you should know they're reporting an estimated Cohen's d. It's our best guess of the population's effect size, our best guess of the population's Cohen d, which again is like a standardized term of the effect size. But we calculate it here with the info that we have, which is our sample, right? It's the estimated version. So we got it from our sample. So just for example, we could go back to our hypothesis in the example before, where the null hypothesis was a population mean of 100. The alternative is that it's not 100. We took a sample. We found a sample mean of 102. If we also calculate that our sample's standard deviation is, say, 3, then we can plug that in to get the estimated Cohen's d, the estimated d. That would be the effect size, which, again, our estimated effect size here is 2, because it's 102 minus 100, right? 102, our sample is 2 above the null hypothesized 100. But then you got to divide that by 3, since that's our SD, right? Our standard deviation of 3. So the estimated Cohen's d is 2 divided by 3, which is 0.66. That is an effect size measure that it's standardized, so it can even be compared to effect sizes in other studies, just to kind of decide, is this a big or a small effect size in general? And remember, a reminder, effect size is separate from whether a hypothesis test turns out to be statistically significant. So it is separate from the p-value question, where we see if our p-value is below the alpha cutoff that we set. So just for example, maybe in this case we used the usual alpha cutoff of 0.05. Maybe we had some tiny sample size of just 4 people. And then when we calculate out, a t-value as part of a t-test or something like that, we would find that the p-value coming out of that isn't low enough to reject. So we would fail to reject the null hypothesis. But in that case, we would be like, welp, there's no evidence of a real effect, in which case we don't want to take this estimated Cohen's d of 0.66 very seriously for anything. So you can see why you need both the p-value to determine if we reject the null or not, like whether we're statistically significant or not, but then you also need an effect size if we do reject the null, just so that we can judge how big of an effect we think it is, now that we think there is an effect. And notice, with the standardized version of effect size, using like Cohen's d, we're just counting how many steps, like how many standard deviations away from the null hypothesis our sample mean m was. Like, if our estimate of Cohen's d wasn't 0.66, but maybe Cohen's d came out to 1, we would just be saying, like, the effect size is 1 standard deviation. What if Cohen's d is 3? then you're saying the effect on average is 3 standard deviations of difference, which would be insanely huge, a huge effect for like anything. And here, our D of 0.66 means an effect size of about 2/3 of a standard deviation, which often would be considered kind of big, right? But how might I judge that? Like, is that big? How meaningful is a particular effect size? And honestly, this is going to be just a matter of interpretation and context. But since we converted it to a standardized measure like Cohen's d, the standardized version, we can use some simplified heuristics that are common in social sciences. So if our estimate of Cohen's d is like 0.2 or lower than that, we often think of that as a small effect. If it's more around 0.5, we might call it often like a medium effect. And if it's at, say, 0.8 or even higher, that would usually qualify as a large effect. But of course, these values, they're just a convention, they're kind of arbitrary, and they just kind of are there to give you a feel for effects. Because in certain fields, in certain contexts, like, I don't know, in medicine or epidemiology, an effect size of 0.1 or even lower than that might still be very important. Honestly, though, a reader is going to have to use their own judgment and compare to the estimated effect sizes of, I don't know, other things that relate to that same topic. So, for example, here's some estimated effect sizes, some Cohen's d's, for a bunch of educational interventions. So we can kind of compare which educational interventions tend to have the largest effect, kind of give the most bang for the buck. So on the far left here, you've got the effect size of mainstreaming versus special education. And that is a D, an estimated Cohen's d of 0.44. The effect size of taking practice tests is around 0.32, as you can see here, and so on. So you can see the biggest effect size is the one near the middle there, which is giving feedback on student performance. That has a pretty huge effect on educational success. Likewise, further right, there's a 0.63 for the targeted interventions for at-risk students. But then on the other hand, look at things like the little ones, like look at the additive-free diet. The estimated effect size of that, even if it turned out to be a real effect, is basically nothing. And individualized instruction, that has a pretty small effect compared to some of these other things, like therapy for test anxiety. The point is, if we calculate something in a standardized way, like using Cohen's d for each study, then we're reporting effect sizes in a way that can be compared, right? A standardized way. We're reporting how many standard deviations worth of improvement do we get from this treatment or this treatment or this treatment, regardless of what we're measuring, so we can compare across anything to anything else using Cohen's d. Now, this is going to be just more of a side note here for the next couple of slides, so don't worry too much about this. But just so you know, there is an alternative measure of effect size, which can be useful for trying to interpret things intuitively. So when we're doing something like, for example, a t-test, where we might be comparing two groups or comparing a group to a hypothesized value, as part of that, we calculate a t-score. It's just kind of part of the process along the way before you get to your p-value. And it turns out, with that number, you can square that t and then divide it by t squared plus what we call the degrees of freedom, which is basically something along the lines of sample size or like sample size minus a bit. But you get a value that we call r squared. Now, r squared is also called the proportion of variance accounted for, as in the proportion of variance in the dependent variable that is accounted for by this thing we're comparing. Like if we're comparing males to females on height, we can calculate r squared as the proportion of variance in height that is accounted for by gender. Like lots of things go into height, gender is one part of that, and this will tell us kind of literally the percentage of height differences that come from gender as opposed to other sources. And the r squared value, it always ranges from 0 to 1. Basically from 0% to 100%. So you can interpret it straightforwardly like a percentage. An r squared value of 0.21 means that this effect, this thing, accounts for 21% of the variation in the dependent variable. An r squared of, if you had 1.0 somehow, that would mean this effect accounts completely for the dependent variable. It's the only thing that determines the dependent variable. And likewise, an r squared of 0.5 means this effect accounts for 50% of the variation in this dependent variable. Now, if you wanted a heuristic for interpreting r squared, you might see sources that call like 0.01, so 1%, a small effect. but say something like 0.09 or 9% of the variance in the DV coming from this effect, they might consider that a medium effect. Whereas 0.25 or 25% of the variance accounted for, that might be a large effect. But honestly, that's just a simplified rule of thumb. In reality, you can judge for yourself since it's pretty clear to interpret an R-squared. If I say 70% of the variation in video game skill comes from practice because I calculated an R-square of 0.7, right? That'd be the 70% for the effect of practice. It's pretty clear how to make sense of that. Okay, before I end, I wanted to give a nice, clear, real-life application where effect sizes were used. And this will be from a Supreme Court ruling a long while ago about violent video games. So first off, this top excerpt, this is where the court concluded that the state's evidence on whether violent games had an effect on kids was not very compelling. They relied on some research by just a few people that it claimed to show a connection between exposure to violent games and harmful effects. But when we don't just cherry pick those few studies from those selective researchers, when we look more critically at the overall evidence, we see that those studies claiming harm were, one, they were based only on correlational evidence, so not strong research designs that show causation, and most of them suffered from flaws in their methodology, it says. So basically, at most, we've got a few cherry-picked studies seeming to show some correlation between violent entertainment and minuscule real-world effects, they say. Notice that phrase, minuscule real-world effects. They're talking about effect sizes here, and they're saying even if the correlation is real, it is small, which is a big limitation. If we also somehow address this causation question, it's still a big limitation on the effect because it's just not much of an effect. And then in the next excerpt here, even if we take for granted Dr. Anderson's conclusion that violent games cause an effect on kids, here's the money quote. Those effects are both small and indistinguishable from effects produced by other media. In his testimony, Dr. Anderson admitted the effect sizes are about the same as that produced by exposure to violent TV, or even cartoons like Bugs Bunny and Roadrunner, or when kids play non-violent games like Sonic the Hedgehog. So imagine that the Supreme Court had made their decision simply on whether some studies had found a statistically significant result and rejected the null hypothesis. If they had made their judgment just based on p-values like that, just based on statistical significance, they might have ended up putting a big limitation on media free speech based on what, in reality, might be an incredibly small effect size. And that's already if we could be sure this was a cause and effect thing in the first place, instead of just a tiny correlation. But okay, we'll stop there. Hopefully this made the idea of effect sizes a little clearer, even if kind of the specific calculations might take some practice for you to get a grasp of. Just remember, we use our sample data to get our best estimate of how big the real population effect size would be, which literally just means looking at our sample and kind of how big of a difference we found in our sample. But then, to make it easier to interpret and compare, we usually divide that by the standard deviation. And that's just so we can report it as Cohen's d, a more standardized, comparable way of reporting the effect size. So if you can get that much to kind of click for you, then you've got the basic idea of effect sizes. And do not forget, this is separate from whether we found evidence that the effect is real. That's a matter of statistical significance, which requires calculating a p-value and seeing if the p-value is below our alpha cutoff, in which case we reject the null hypothesis, we say there's a statistically significant effect. Only then would you report the effect size so people can judge an estimate of how big of an effect it is that you've discovered.